Hey guys, we're back in week 7. So for our first set of notes, we're going to talk about the logarithm graph. So this is going to be our final parent function. This is going to be the last time that we're going to be graphing something. And as you already know, you know that we always introduce what the parent function looks like, and then we talk about the transformations that haven't changed all year long. So here we go. We know that the logarithmic parent function is the inverse of our exponential parent function. We've been talking about that. So just to refresh our memory, we're going to graph what our exponential parent function looks like, and then we'll use that information to help us graph our logarithmic parent function. So remember in exponentials, we talked about how our base needs to be positive number, right? It can be greater than 1, which would show growth, or it can be between 0 and 1, which would show decay, but we can never have a negative base. So that's why in our log functions, we can't have a negative base, which also means we cannot have that negative argument. We talked about that a couple weeks ago. So in the first set of graphs, we're going to make our base greater than 1. So this would be showing a growth in the exponential graph. So just as you remember, if our base is greater than 1, our point would be 0, 1, because anything raised to the 0 power is going to give us 1. We would have 1, whatever our base is, 2, whatever our base squared is, and then negative 1, 1 over that base. And we don't know what our base is, but that's what we would get, right? Exponential graphs always had a horizontal asymptote, and that horizontal asymptote was at y equals 0. So here's our horizontal asymptote. We could plot those points, 0, 1, 1 whatever our base is, 2 base squared, negative 1, 1 over that base, and we would get that exponential growth looking graph. Our domain was always negative infinity to positive infinity, and then our range, if there was no transformations, was always 0 to infinity. Remember, our horizontal asymptote kind of denoted where that range was going to start. If you shifted up or down that horizontal asymptote, then that's where the range would begin. Okay, so because the log and the exponential graphs are inverses of each other, you know that a characteristic of inverses is that the points in the ordered pair simply switch. Your x's and y values switch places. So over here on the right hand side, notice we have log base b of x. B is still greater than 1. So instead of the point 0, 1, now we're going to have the point 1, 0. Instead of 1, the base, we'll have whatever the base is, 1. We'll have the base squared, 2. We'll have 1 over the base, negative 1. And instead of a horizontal asymptote, now we're going to have a vertical asymptote. And our vertical asymptote is going to be going through at x equals 0. Here it is. So I can plot the points 1, 0, whatever my base is, 1, whatever my base is squared, 2, etc., etc. And so we get this shape for our logarithmic function. Notice here our domain is always going to be the positive numbers, because remember, x is where my argument is. If I look at the parent function, log base b of x, x is the argument. That number always needs to be positive. So it's going to be from 0 to infinity. That also is where my vertical asymptote is. Range this time will be from negative infinity to positive infinity. And remember, another characteristic of inverses is that the domain of one is the range of the other, and the range of one is the domain of the other. So in exponentials, our domain was always negative infinity to positive infinity. So in logarithmic graphs, our range is always going to be from negative infinity to positive infinity. Always, always, always. Okay? All right. So that's what it looks like if our base is greater than 1, which is majority of the time what you're going to see in logarithmic functions. It's very rare that we have a base in a log function that's between 0 and 1. However, it could happen. So if we look at the exponential graph, if our base is between 0 and 1, we know that's going to be showing decay. Our points are still 0, 1, 1, whatever our base is, 2, whatever our base squared is, and negative 1, 1 over our base. It's just that base is a number that's between 0 and 1. Let's say it's a third or a half or whatever. So we still have that horizontal asymptote at y equals 0. 0, 1, 1, whatever our base is. And so we get that decay model. Domain was always negative infinity to positive infinity, and our range here was still 0 to infinity. So over here, we're doing the same thing. If we just happen to have a base that's between 0 and 1, our points are still going to be 1, 0, whatever our base is, 1, whatever our base squared is, 2, and then our 1 over the base, -1. Okay, so in plotting that, we'd still have our vertical asymptote at x equals 0. 1, 0, sorry. 1, 0 would be here. Oh, sorry, there's a fly on my iPad. Okay. And then our base, 1. So remember, this is whenever our base is never between 0 and 1. So it might be somewhere here. Base squared might be somewhere there. And then it would show this model here. Domain is still going to be from 0 to infinity because our argument can never be negative. And then range is always going to be negative infinity to positive infinity. So we're really utilizing those characteristics of inverses here to graph the logarithmic parent function. Okay, so let's go into some actual examples here. Number 2, it says sketch the graph of f of x equals log of x. So notice here the base is not listed. So when the base is not listed, it has a base of, do you remember? 10. Good job. So here we go. This is a log function. So we're going to have the point 1, 0, whatever our base is, 1, our base squared, 2, and we know that's a really large coordinate location that's not going to fit on our graph, and then 1 over our base, -1. Because this is a log function and it hasn't been transformed, we're going to have that vertical asymptote at y equals 0, and so I can just plot these points. 1, 0, 10, 2, and then 1 over 10, -1 would be really close here. Really hard to graph those points, but it gives you that shape of the graph. Okay, domain still from 0 to infinity, and then range negative infinity to positive infinity. Always, always, always. Okay, over here now we have the natural log of x. Well, what's the base of a natural log? E. Good job. And do you remember E's approximation? It's about 2.7, right? 2.718. And so for the purpose of graphing, we can just go with 2.7. It's between 2 and 3, right? We're not going to be perfect, but that's okay. We're going to have the point 0, 1. We're going to have the point E, 1. So that would be about 2.7, 1. We would have the point E squared, 2. Well, E squared is about 7.3. And then we would have the point 1 over E, which is about 3.37, excuse me. 1 over E, about 0.37, and then -1. Still have that vertical asymptote at x equals 0. 2.7, 1 would be somewhere here. 7.3 is going to be a little bit off that graph. 2 would be there. And then 0.37, -1 would be somewhere there. And so we get that shape of that logarithmic graph. Domain, 0 to infinity, range negative infinity to infinity. Okay, so really not that bad. If you know how to graph your exponential, all you have to do is switch those coordinate locations around, and now you got your logarithmic. So instead of the horizontal asymptote for exponential, you got the vertical asymptote for logarithmic. Okay, and so here again is our beautiful transformation little chart that we've seen 8 times this school year. I've gone ahead and plugged it in already because you should already know what those things look like. Remember in exponentials, the shift left, right, up, and down didn't give us a point on the graph. It was like our new origin point. Same thing here for logarithmic because they're inverses of each other. So if I shift up, down, left, right, that's going to be my new center, quote unquote, or my new origin for the graph. So all those points will be coming from that location. So let's go ahead and see some with transformations listed. So I like to list out who my base is, what transformations have been applied, and then, write down the points. So here my base is 2, right? That is not a part of the transformations. I need to identify what that base is. It's 2. Now I see that it has a vertical stretch of 3. I see that I'm going left 4, so that left 4, and I'm going down 1. So that left 4 down 1 is like my new center. It's my new origin. So I'm going to go ahead and put that little X or that star there just like I did in exponentials, right? In exponentials, we located that new origin and then we went ahead and put our horizontal asymptote. So for logs, we can locate our new center and then we can go ahead and put our vertical asymptote. Okay. So with a base of 2, starting from the point -4, -1, we would have the point 1, 0, our base, 1, our base squared, 2, and then 1 over our base, -1. So from that point, -4, -1, I would be plotting those points. However, I still have a vertical stretch that needs to be applied. A vertical stretch would obviously be applied to those numbers here. So I need to multiply my y values by 3. Well, 0 times 3 is still 0. 1 times 3 is 3. 2 times 3 is 6. -1 times 3 is a -3. So now I'm plotting those points. So from -4, -1, I'm going to go right 1 up 0, which is here. I'm going to go right 2 up 3. 1, 2, 3. I'm going to go right 4. 1, 2, 3, 4 up 6. 1, 2, 3, 4, 5, 6. And then I'm going to go right 1/2 and down 3. 1, 2, 3. And so there I get that shape of that logarithmic graph. I can immediately tell my domain. Remember, those are the x values. So that's going to be from -4 all the way to infinity. That's going to be -4 to infinity. That's always going to be a parenthesis there because I cannot use an x value of -4 because if I do, that would make my argument 0, and I can't have an argument of 0 or anything less than 0. So it's always going to be a parenthesis there, not a bracket. Range, as we already know, always going to be from -infinity to a positive infinity. Let's try one more time. When you look at part B, I'm hoping you know exactly what we need to do first. Maybe you're thinking identify the base. That's totally fine. I love it. But what's another thing you need to look out for? If there's anything in front of the x, we have to factor it out. We've been doing that the whole entire year, right? So I'm going to go ahead and just rewrite it right now. Still negative log base 3. Factoring out that 2, I'm going to be left with x plus 5 and then plus my 4 at the end. Okay, so I know my base is 3. And so now I need to list out my transformations. Well, the negative in front means I'm reflecting over the x-axis, so reflect over x-axis. The 2 inside of the parentheses tells me I have a horizontal compression. Remember, anything above 1, greater than 1, is going to be a compression for horizontal. I'm going to the left 5, and I'm going up 4. So left 5, up 4. That's going to be my new origin, my new center. So I can go ahead and mark that off. Left 5, up 4 would be right here as my new center point. Because that's there, I can go ahead and mark my vertical asymptote. Okay, so from the point -5, 4, I'm going to go 1, 0. Whatever my base is, 1, my base squared, 2, 1 over my base, -1. So now I need to change those numbers because I have the reflection over the x and the horizontal compression. Reflection over the x-axis is going to take anything in the first 2 quadrants and flip them down to the 3rd and the 4th quadrant, or vice versa, right? So that's affecting the sign of my y values. So 0 will stay the same, obviously. Let me change colors. This will now be a -1, a -2, and a +1. That's taking care of the reflection over the x-axis. The horizontal compression is going to affect those x values, the rights and the lefts. So I'm going to multiply those by a half. So this is now 1/2. This is now 3/2. This is now 9/2. And this is now 1/6. Okay, so now from the point -5, 4, I can go right 1/2 up 0. I can go right 3 over 2, which is 1.5, and go down 1. I can go right 9 over 2, which is 4.5. So 1, 2, 3, 4.5. Down 2, 1, 2. And I could go right a sixth up 1, which would be really tiny. And so now I see this shape of the graph because it's been reflected and because it's been horizontally compressed. Domain, so those are those x values. That's going to be, that vertical asymptote is going to kind of help you decide where your domain starts. Well, that would be at -5, and it would go all the way to infinity. My range, always negative infinity to positive infinity. Okay? And then the last two. It wants us to find the domain, but without graphing. So we need to understand some characteristics about logs here. Okay? Earlier, just in this and last week, we talked about how the log function cannot have a negative argument. It can't have a negative base, so therefore it cannot have a negative argument. So our argument, what's inside of the parentheses, always needs to be greater than 0. It cannot equal 0 because a base raised to any number will never equal 0. So that means -7x plus 2 needs to be greater than 0. Now, a is something that you could graph if you had to. You would factor out the -7, apply those transformations, and you could graph it. No big deal. But when you look at something like part B, look at your argument. I would not expect you to graph that, okay? No way, Jose. So we're going to use that same thing and say our argument needs to be greater than 0. Cannot equal 0. It has to be bigger than 0. It has to be positive. So we're just solving inequalities. In part A, that's an easy linear inequality that you can solve. I would subtract my 2, get -7x is greater than -2, dividing by the -7. Remember, when you divide by a negative number, what happens? You have to flip your sign. -2 divided by -7 is a positive 2 over 7. So though I want the x's that are less than 2 over 7. So for my domain, that means it would be from -infinity to 2/7. That would be my domain, which makes sense. That negative on the inside of the parentheses is a reflection of the y-axis. Factoring out that 7, it makes sense graphically for me in my head. Now over here for part B, setting our argument greater than 0, I'm going to have to factor the left-hand side. First thing I look out for is a GCF. It doesn't have one. So now I need to multiply my A value, my C value. So 3 times -6 is -18. I need factors of -18 that add up to -7. That's going to be a -9 and a +2. So I'm going to rewrite my function, or my quadratic. 3x squared minus 9x plus 2x minus 6 greater than 0. I haven't changed anything, but now I can factor by grouping. So the GCF in the first two terms is a 3x, leaving me with x minus 3. GCF in the last two terms is a +2, leaving me with x minus 3, still greater than 0. So I get 3x plus 2 times x minus 3 is greater than 0. So if you remember when we did inequalities with quadratics back in semester 1, we need to find the zeros, plot them on the number line, and figure out where is it positive and where is it negative. Well, the 0 from the first factor is going to be a -2/3. The 0 from the second factor is a +3. So I need to pick a test point on the left, in the middle, and on the right. I'm going to go ahead and pick the middle first because that's easier for me, because a good test point in the middle is 0. I have a negative and a positive, so I know 0 is in the middle. Somewhere between them, I should say, not in the middle. But so if I plug in 0, let me change colors. If I plug in 0 for x in both of those factors, I would get 3 times 0 is 0, plus 2 is 2, that's a positive number, times 0 minus 3 is -3. 2 times -3 is a negative number. Negative is going to be down here. Is a negative number greater than 0? So this is no. This is a negative value. None of this between the -2/3 and the 3 is going to be shaded because it doesn't apply, doesn't make that statement true. However, if I plug in a number on the left of -2/3, so maybe -5 or -10 or whatever, let's say I plug in a -5 for x. 3 times negative 5 is negative 15 plus 2 is still a negative number. Negative 5 minus 3 is a negative number. Negative times negative is positive. Positive is greater than 0, so this part will be shaded. Now I need to pick a test point on the right side of 3. Let's say I pick 7 or 10 or 5 or whatever. Let's say I pick 10. Okay, make it a little bit easier. If I plug in 10 for x, 3 times 10 is 30 plus 2 is 32. That's a positive number. 10 minus 3 is a positive number. So positive times positive is positive. So this is also greater than 0. So that means that the domain for this function, would be from negative infinity to negative 2/3 and from 3 to infinity. And there you have it.